Welcome to Science for Sleep. Tonight, we're exploring a question so strange, so subtle, that physicists themselves still argue about it quietly decades after its discovery. A question that seems almost impossible, yet refuses to go away. Can observation itself change reality? And more specifically, can your focus alter the universe around you? At first, this sounds like philosophy, or science fiction, or something pulled from a late-night thought spiral. But this question comes directly from experimental physics, from real laboratories, from measurements that behave differently when they are watched. To understand how we arrived here, we have to step away from everyday intuition. Because at the smallest scales of existence, the universe does not behave the way common sense expects. In your daily life, objects exist whether you look at them or not. A chair remains a chair. A clock continues ticking. The moon stays in the sky even when no one is watching. But when scientists began probing reality at the level of atoms and particles, something unsettling appeared. Particles did not behave like solid things. They behaved like possibilities. Electrons, photons, and other quantum particles do not have fixed positions until they are measured. Before observation, they exist in a spread-out state, a cloud of probability. Not here, not there, but everywhere they could be. This strange behavior became impossible to ignore in one famous experiment. An experiment simple enough to explain, yet deep enough to unsettle everything we thought we knew. It's called the double-slit experiment. Imagine firing tiny particles of light, photons, at a wall with two narrow openings. Behind the wall is a screen that records where the particles land. If light were made only of particles, you would expect two clusters on the screen, one behind each slit. But that's not what happens. Instead, the screen fills with a striped pattern, an interference pattern, the kind you would expect from waves overlapping each other. This suggests that each particle somehow travels through both slits at once, interfering with itself, behaving like a wave. Now comes the part that changes everything. When scientists place detectors to observe which slit the particle goes through, the interference pattern disappears. The particle behaves like a particle again. Simply knowing which path it took changes the outcome. Observation collapses possibility into fact. This is not metaphor. This is not interpretation. This is what the math predicts, and what experiments confirm. The universe behaves differently when it is observed. Naturally, this raised an uncomfortable question. What counts as observation? A machine? A measurement? A conscious mind? Physicists argue about this to this day, because the equations don't clearly say. They only say that interaction that extracts information causes collapse. Some interpretations suggest that consciousness plays no role. Others leave the door slightly open, and a few leave it wide open. This is where the quantum observer effect enters public imagination. Often misunderstood, often exaggerated, but rooted in something undeniably real. The observer effect does not mean that your thoughts can magically bend spoons. It does not mean wishing creates outcomes. Science is careful here, very careful. But it does mean that reality, at its foundation, is not independent of interaction. It is relational. Particles do not exist in definite states until something interacts with them, until information is exchanged, until the universe takes note. Now pause for a moment, because this is where the idea becomes quietly profound. If reality needs interaction to take shape, then observation is not passive. It is participatory. This idea was unsettling even to the founders of quantum mechanics. Albert Einstein famously resisted it. He believed the universe should exist independently. God does not play dice, he said. Yet experiment after experiment suggested otherwise. Randomness appeared fundamental. Certainty evaporated. One physicist, John Wheeler, proposed something radical. He suggested the universe is a participatory system, that observers are not separate from reality, but woven into its unfolding. In this view, the universe does not fully exist until it is observed, not just locally, but globally. Wheeler even suggested that the universe might be shaped retroactively by observation, that measurements may now help define the past. This is not science fiction. Delayed choice experiments have demonstrated behavior that appears to confirm this possibility. Reality seems flexible, not chaotic, but responsive. So the question shifts, not does reality exist, but how does reality become definite? And where do we fit into that process? Before we go further, notice how calm this question actually is. It doesn't demand belief. It doesn't threaten stability. It invites curiosity. In the next part, we'll explore what observation actually means in physics, why it doesn't require mysticism, and how information may be more fundamental than matter itself. For now, let the question rest gently. No need to solve it. The universe has time. When physicists say that observation changes reality, they do not mean what the word observe usually implies. They are not talking about looking. They are talking about interaction. In quantum physics, observation means that information is extracted from a system. Something touches something else. Energy is exchanged. A measurement is made. This distinction matters because it removes the idea that human eyes or thoughts are automatically responsible for quantum effects, at least at first. When a detector measures a particle, it becomes entangled with it. The particle's possible states collapse into a single outcome, not because the detector is conscious, but because information has been recorded. This leads to one of the most important ideas in modern physics. Information may be more fundamental than matter. Matter behaves strangely. Energy transforms. But information appears to be conserved, never destroyed, only transferred. Black hole physics reinforced this idea. For decades, scientists believed information falling into a black hole was lost forever. Then came the information paradox, and eventually, the realization that information must be preserved, even in extreme conditions. This shifted how physicists think about reality itself. The universe may not be made of particles. It may be made of relationships. In this view, particles are not objects. They are events, interactions, moments where information becomes definite. So when a quantum particle exists in a superposition, it is not undecided. It is relational. Its state depends on what it is interacting with. Observation, then, is not an act performed by a mind. It is a process embedded in the universe. But this creates a deeper puzzle. If observation is interaction, and everything interacts with everything else, why doesn't reality collapse constantly? Why does the world appear stable at large scales? The answer lies in a process called decoherence. Decoherence explains how quantum possibilities fade into classical reality. When a system interacts with its environment, air, light, heat, its delicate quantum states become scrambled. Interference disappears. Certainty emerges. This happens extremely fast, faster than thought, faster than perception. By the time you see an object, it is already classical, already settled, already collapsed. This is why we don't see chairs in superposition, why the moon stays where it is, why everyday reality feels solid. So far, consciousness has not entered the equation, and many physicists stop here. But some don't, because decoherence explains how possibilities disappear. It does not explain why one outcome is experienced instead of another. The equations still describe multiple possibilities, yet you experience only one. This leads to interpretation, and quantum mechanics has many interpretations, each trying to explain what reality is actually doing beneath the math. One interpretation says all outcomes happen. Every possibility branches into a new universe. This is the many worlds interpretation. In this view, observation does not collapse reality. It divides it. Another interpretation says the wave function collapse is real, a physical process, triggered by measurement, but not fully understood. Then there are interpretations that treat consciousness as essential, not proven, not dismissed, just unresolved. Physicist Eugene Wigner proposed that consciousness may be what completes the measurement, that without awareness, reality remains indefinite. This idea is controversial. Many physicists reject it. Others remain quietly open. Why? Because consciousness itself remains unexplained. No physical theory has yet shown how subjective experience arises from matter. Neurons fire. Signals propagate. But experience appears. So some researchers ask a forbidden question. What if consciousness is not produced by the brain? What if the brain tunes into it? In that case, observation might involve more than interaction. It might involve experience. This is where science edges into philosophy, and where speculation begins. But speculation does not mean nonsense. It means curiosity beyond current tools. For now, keep this grounded truth in mind. Quantum mechanics does not say that thoughts create reality, but it does say that reality is not fully formed without interaction. And it leaves open one quiet possibility: that awareness may not be as separate from the universe as we assume. In the next part, we'll explore focus, attention, and whether mental states can influence physical systems. Not magically, but subtly, statistically, and experimentally. There's nothing to believe yet, only something to notice. Focus feels simple. You pay attention. You notice something. You let go. But neurologically, focus is not passive. It is an active process. Energy flows. Neural networks synchronize. Signals amplify. When you focus on something, your brain changes its state. Oscillations align. Noise decreases. Signal clarity increases. This is not philosophy. It is measurable. Electroencephalograms show shifts in brain rhythms during attention. Functional imaging reveals coordinated activity across distant regions. Attention physically reorganizes neural activity. So the question becomes subtle. Not, can thoughts change reality? But, can changes in physical brain states influence physical systems? At everyday scales, the answer appears to be no. Your focus does not bend objects. It does not override gravity. It does not rewrite chemistry. But at the edge of measurement, at the threshold where probabilities rule, the question becomes more interesting. In quantum systems, outcomes are statistical. You do not predict single events. You predict distributions. This means influence, if it exists, would not be dramatic. It would be faint, directional, a bias, not a command. Some experiments have attempted to test this idea. Carefully, cautiously, often controversially. One such area involves random number generators, devices designed to produce truly unpredictable sequences. In several long-running studies, participants were asked to focus their intention on influencing these systems, to nudge randomness slightly one way or another. Results were small, often barely above noise, sometimes disappearing, sometimes reappearing. Critics argue methodological flaws. Supporters argue cumulative patterns. No consensus exists, which itself is telling. Another area involves quantum biology, where quantum effects appear to operate inside living systems. Photosynthesis uses quantum coherence. Bird navigation may rely on quantum entanglement. Enzymes exploit tunneling. Life, it turns out, may already operate near quantum limits. This opens an intriguing possibility that biological systems might interact with quantum processes more directly than we assumed. Still, this does not mean consciousness collapses wave functions. It means living systems may be exquisitely sensitive to subtle effects. Focus, then, may be less like a force, and more like a tuning mechanism, not creating outcomes, but selecting pathways. This idea echoes ancient traditions. Meditative practices describe attention as shaping experience, not the world itself, but how reality unfolds to the observer. Modern neuroscience agrees. Attention filters perception. Experience changes. Meaning shifts. Even if the external world remains unchanged, the experienced universe becomes different. This raises a deeper question. If reality is partly defined by information, and experience is information-rich, then perception may not be secondary. It may be fundamental to how reality is structured at human scales. Not altering atoms, but altering meaning, probability, relevance, and meaning matters. In physics, observation defines outcomes. In life, attention defines reality. The two ideas begin to echo each other. Not identical, but resonant. Some theorists suggest that consciousness evolved precisely because it can model possibilities, simulate futures, evaluate paths. In this sense, focus does not change reality directly. It changes which realities you move toward. Choice emerges, not as magic, but as navigation. There is a quiet idea in physics that rarely appears in headlines, an idea that feels strange but persistent. What if the universe requires observers to exist in a meaningful way? Not observers as humans, not minds with names and faces, but systems capable of registering information. Physicist John Wheeler called this the participatory universe, a universe that is not complete without participation. In this view, reality is not a static structure. It is an ongoing dialogue between what exists and what is known. Wheeler imagined a universe where acts of measurement help bring the universe into being, not creating it from nothing, but refining it from possibility. This idea becomes especially strange when applied to cosmology. Early in the universe, before stars, before planets, before life, who was observing? If observation is necessary for reality to crystallize, how did the universe begin? One answer is unsettling. Perhaps observation does not require consciousness, only interaction. Particles observe each other, fields interact, information flows. Reality then self-observes. But Wheeler suggested something deeper, that observers at the end of time might complete the universe's history, that present observations help define the past. This is not mystical thinking. Delayed choice experiments support this possibility. In these experiments, the decision to observe a particle's path can be made after it has already passed the measurement point. And yet the outcome behaves as if the particle always knew how it would be measured. Time itself becomes flexible, not linear, but relational. Events do not simply happen and then get recorded. They remain uncertain until observation fixes them. This idea blurs the boundary between past and present, between cause and effect. Some physicists argue this means the universe is fundamentally timeless. That time emerges from relationships, not flow. In this framework, consciousness becomes intriguing, not as a cause, but as a participant. If conscious systems are especially efficient at extracting information, they may play a role in shaping experienced reality, not by forcing outcomes, but by collapsing complexity into coherence. This leads to a controversial idea, that consciousness may be necessary for a universe that knows itself. Not proven, not required, but not easily dismissed. Some thinkers go further. They propose that the universe is structured to give rise to observers, that laws of physics appear finely tuned for complexity, life, and awareness. This is known as the anthropic principle. In its weak form, it simply states that we observe a universe compatible with our existence. In its stronger form, it suggests the universe is somehow oriented toward observation. Again, no proof, but the question persists. If observation is fundamental, and consciousness observes, then awareness may not be accidental. It may be an emergent property the universe uses to examine itself. This idea appears in philosophy, in mysticism, and now, quietly, in physics, not as belief, but as possibility. Before moving further, let's ground ourselves. Quantum mechanics does not claim the mind creates reality, but it does undermine the idea of a fully independent, objective universe. Reality appears relational, dependent on interaction, defined by information exchange. Consciousness, at minimum, is a master of information. That alone makes it relevant. Quantum physics attracts stories, not because it invites fantasy, but because it resists intuition. When something defies common sense, the mind fills the gap. And over time, those gaps become beliefs. You may have heard claims like, "Your thoughts create your reality." "The universe responds to intention." "Focus collapses the wave function." These ideas sound scientific. They borrow language, but they often drift far from evidence. This does not mean they are malicious. It means they are human. Science demands something difficult: restraint. Physicists are careful with words like cause and effect. They know that quantum mechanics describes probabilities, not desires. There is no experiment showing that belief alone alters physical outcomes beyond chance. No repeatable study demonstrating that consciousness overrides measurement devices. When studies suggest small effects, they remain controversial. And controversy is not proof. But here's the important part. Debunking exaggeration does not erase wonder. Reality is still deeply strange. Particles still exist as possibilities. Time still bends. Information still shapes outcomes. The universe does not need mysticism to be mysterious. At the same time, science also recognizes its limits. There is no theory of consciousness. No explanation for why experience exists at all. No equation that produces awareness. So scientists stay cautious, open, but disciplined. This balance matters, because wonder without rigor becomes fantasy, and rigor without wonder becomes sterile. Some ideas live at the boundary: simulation theory, participatory universes, observer-dependent reality. They are not accepted facts, but they are not dismissed. They remain hypotheses, waiting. And waiting is part of science. Here is a calmer truth. Your focus absolutely alters your reality, your perception, your emotional landscape, your memory formation, your future decisions. That influence is real, measurable, profound. Whether it extends beyond the brain remains unknown. But even uncertainty has value. It keeps the question alive. At the deepest level we can measure, reality is not made of things. It is made of relationships. Atoms are not solid. They are patterns, vibrations and fields, probabilities held together by forces. Every particle is an excitation, a ripple in something more fundamental. Quantum field theory tells us that empty space is not empty. It seethes with activity. Virtual particles appear and disappear. Energy fluctuates. This means the universe is not a stage where matter performs. The universe is the performance. When we say a particle exists, we really mean that a set of probabilities has stabilized. Measurement is the act of stabilization. This is where the observer enters again, not as a thinker, but as an interaction. A detector does not care about belief. It only cares about coupling. When systems interact, information transfers. And information defines reality. This leads to a powerful idea. That reality is informational at its core. Physicist John Archibald Wheeler summarized it as it from bit, meaning that physical existence arises from information. If this is true, then observation is not optional. It is foundational. But observation does not require consciousness, only difference-making. The universe is constantly measuring itself. Particles collide. Fields interact. States resolve. Consciousness enters later, as a refined form of information processing. Human awareness may be a high-level interface, not the engine. Still, interfaces matter. They shape what is seen. Different observers extract different information. Different measurements reveal different realities. This is not subjective truth. It is contextual truth. A photon can behave as a wave or a particle, not because it decides, but because the context demands one description over another. Reality adapts to questions, not intentions. This distinction is subtle and important. Your focus does not command the universe, but it shapes the questions you ask, and questions determine answers. This applies everywhere, in science, in life, in perception. When you attend to fear, the world sharpens. When you attend to calm, the world softens. Not because reality changed, but because the informational slice you're accessing has changed. This is the real power of focus. It does not bend atoms. It bends experience. And experience is the only universe we ever know. Time feels obvious, a flow, a direction, a before and after. But physics tells a quieter story. At the fundamental level, the equations do not care about time's direction. They work the same forward and backward. This creates a problem. If the laws are timeless, why does time feel like it moves? One answer is entropy, the tendency for systems to move from order to disorder. This gives time an arrow, not because the universe demands it, but because complexity accumulates. Quantum mechanics complicates this picture. In certain experiments, effects appear to precede causes, not in a dramatic way, but subtly. Delayed choice experiments show that present measurements influence how past events are described, not rewriting history, but determining which version of history becomes real. This distinction matters. The past is not a fixed recording. It is a set of possibilities constrained by present information. Until measured, those possibilities remain open. This does not mean the universe is unstable. It means it is relational. Events gain meaning through context. Causality still holds. Signals do not travel faster than light. Time travel is not happening. But description flows differently than intuition. Reality is less like a movie, and more like a story being edited as it's read. Observation does not change what happened. It changes what counts as what happened. This sounds philosophical, but it is experimentally grounded. Now consider consciousness again. The mind experiences time as a sequence, moments flowing, memory forming a narrative. But memory is selective. It edits, fills gaps, reconstructs. Your experience of time is not raw data. It is interpretation. This mirrors physics. Both mind and universe assemble reality from information. Neither accesses an objective timeline, only relational snapshots. So does focus alter reality? It alters which slice of time you inhabit, which memories dominate, which futures feel possible. Not because the universe obeys thought, but because attention organizes experience. The observer effect reminds us of something subtle. That reality is not just out there, it is also processed. After everything we've explored, the experiments, the equations, the interpretations, the myths, we can answer the question carefully. Can your focus alter reality? Not in the way movies promise. Your thoughts do not command particles. Belief does not override physics. The universe does not bend to intention. But focus is not powerless. Focus selects. Focus organizes. Focus shapes experience. In quantum mechanics, observation does not mean awareness. It means interaction, measurement, information exchange. Reality resolves when systems interact, not when they wish. Yet consciousness plays a unique role. It is where reality becomes known, felt, remembered. The universe exists whether or not you watch it. But meaning does not. Meaning requires experience. This is where science and philosophy meet quietly. Physics describes what happens. Consciousness describes what it is like. Neither replaces the other. The observer effect reminds us that certainty has limits. That objectivity is contextual. That reality is subtler than solidity. And that humility is built into the universe. There will always be unknowns. Why anything exists at all. Why experience feels like something. Why laws are as they are. These questions remain open, not as failures, but as invitations. And perhaps that is the deeper lesson. The universe does not need us to exist, but it allows us to wonder. And in that wondering, reality becomes richer. As you rest now, let these questions soften. They do not need answers tonight. The universe will still be here, quiet, patient, and when curiosity wakes again, so will the questions. For now, let awareness fade gently. Let focus loosen. Let the observer rest. Thank you for spending this time with Science for Sleep. Until the next question, good night.